Okay, so let's dive into one of the most exciting, most impactful innovations happening in AI right now, retrieval augmented generation. Yeah, I know, it's a mouthful. Most people just call it RAG. But the idea behind it is actually super simple and honestly brilliant. What if we could give our AI a library card, a way to access specific, up-to-the-minute information whenever it needs it? Let's break down how that actually works.
But before we jump into the solution, we got to understand the problem it's trying to solve. You see, large language models, as incredible as they are, often act like, well, like very confident guessing machines. I mean, we've all been there, right? You ask a chatbot a perfectly reasonable question, and it gives you this answer that sounds so convincing, so plausible, but it's just completely, totally wrong. It's that exact moment of frustration that RAG is designed to eliminate.
And this whole issue really boils down to two core problems. The first one is what we call hallucination, which is just a fancy word for when the model makes stuff up that sounds correct. The second big one is the knowledge cutoff. You have to remember, these models are essentially frozen in time. They're stuck with only the data they were trained on. So it can't tell you about something that happened last week because for the AI, it literally hasn't happened.
So how do we fix this? How do we take these powerful models and make them more reliable, more current? Well, it's simple. We give them a library, and that is the whole idea behind the RAG solution.
The absolute game changer here is that RAG connects the language model to external, real-world knowledge before it even tries to formulate an answer. So instead of just reaching into its static, pre-trained memory, the AI actively goes out and looks up facts, figures, and recent events from your own documents or databases. This grounds the model in reality, making its answers way more accurate and, frankly, trustworthy.
The process itself is actually pretty straightforward. It all happens in 3 key steps. First, when you ask your question, the system retrieves the most relevant bits of information from its knowledge base, its library. Second, it augments your original question by stuffing all that new context right alongside it. And finally, it feeds that whole package to the language model to generate a much smarter answer. Think of it like this. It's the difference between a closed-book test based purely on memory and an open-book exam where you can look up the facts.
Okay, so that's the big picture. But now let's peek under the hood a little bit. Let's look at the 3 core components that really make this engine run. This is where the magic really happens.
The very first piece of the puzzle is something called chunking. You can't just feed a 100-page PDF to a model and hope for the best. You have to break it down into smaller, digestible, meaningful pieces. A great way to think about it is like a chef deciding on portion sizes. You want the chunks to be big enough to contain useful context, but small enough for the model to process them efficiently.
And, you know, chunking isn't just about randomly splitting up text. It's a real strategic decision. As this quote from Microsoft Learn points out, you have to balance things like your budget, the quality you're aiming for, and the speed you need. A really sophisticated chunking strategy might get you slightly better results, but it's also going to cost you more in engineering time and processing power. It's that classic engineering trade-off.
All right, next up, embeddings. Now, this one can sound a little abstract, but stick with me, because this concept is incredibly powerful. An embedding is a process that turns a chunk of text into a long list of numbers, what we call a vector. But it's not a random list. This vector captures the meaning of the text. You can think of it as giving each piece of text a unique address in a giant invisible map of meaning, where similar ideas end up as neighbors.
To really make that concrete, just imagine 2 sentences. The cat sat on the mat, and a feline rested. They mean pretty much the same thing, right? So on our meaning map, their numerical addresses would be plotted super close to each other. But a totally different sentence, like Python is a programming language, is about a completely different topic, so its address would be way over on the other side of the map. It's that distance, that mathematical relationship that lets the AI understand context and meaning.
So you've got all your text chopped up into chunks, and you've turned every one of those chunks into a numerical vector. Now you have potentially millions of these things. How in the world do you search through them all instantly? Well, that's where our third component comes in, the vector database. This is a special kind of database built for one single purpose, to store and search through these meaning vectors at lightning speed. It's like a super-powered, magically meaning-aware card catalog for your AI's entire library.
So we've covered the theory, but here's the best part. You don't have to build all of this from scratch. Not even close. There's an incredible ecosystem of open-source tools and frameworks out there that make building RAG systems more accessible than ever before. Let's take a look at a few of the most popular choices.
2 of the biggest names you're going to hear over and over are LangChain and LlamaIndex. LangChain is kind of like the Swiss Army knife for building with LLMs.
It's fantastic for creating really complex, multi-step AI agents and workflows. Llama Index, on the other hand, is much more data-centric. Its whole focus is on being the best at connecting all sorts of different data sources. We're talking plain text, APIs, even SQL databases directly to your language model.
And what about the model that actually creates the embeddings? Well, you guessed it, more trade-offs. You could use a massive proprietary model from a big company. You'll get incredible precision, but it's going to be expensive. Or you could host your own open-source model. A powerful GPU-hosted model will give you great precision, while a cheaper CPU-based one will be faster and less expensive, maybe at a slight cost to precision. It really just comes down to that classic balancing act between your need for accuracy, speed, and of course budget. Okay, so you've picked your tools, you've chunked your data, you've built your RAG system, it feels amazing, but now comes the most important part, the reality check. How do you actually know if it's any good?
This, right here, is the million-dollar question. It is not enough to just get an answer. You have to know if that answer is accurate, if it's relevant, if it's trustworthy. Remember, building the system is only half the battle. Making sure it actually works well, that's the other half. So how do we measure quality in a structured way? Well, we can borrow a really nice framework from LangChain's own documentation that breaks it down into 4 key areas. First, correctness. Is the final answer factually right? Simple. Second, relevance. Did it actually answer the user's question, or did it go off on a tangent? Third, groundedness. Is the answer supported only by the information it found in the library, or did it start hallucinating and making stuff up again? And finally, retrieval relevance. Did the system even pull the right documents from the library in the first place? If you can nail all 4 of these, you've got a high-quality RAG system. So at the end of the day, RAG is what transforms a general-purpose AI into a genuine specialist, an expert that's armed with a curated library of your specific knowledge. It tackles hallucinations, it keeps the AI current, and it makes it a genuinely powerful tool for everything from smarter customer support bots to deep enterprise research. And that brings me to one final question for you to think about. Your AI now has a library card. What are you going to teach it first?